You are watching DHTV from California State University, Dominguez Hills.
Hi, I'm Dr. Pamela Kreiser, and welcome back to NCR 507, which is Research Design and Interpretation. Now today we're going to talk about a very important test that is run so often in statistics. We're going to talk about the correlation, and specifically we're going to examine the Pearson correlation. So as we look at this test, we want to start by talking about some of the tests that you and I have reviewed in previous sessions. So let's take a look at the chart and get a sense of where the landscape falls related to correlation. Now we can see from this chart that it has a very familiar look to it because we've seen this chart before. It helps us understand what kind of test to use when we have certain kind of independent variables and when we have certain kind of dependent variables. So you can see in the chart that there are two areas that we care about in order to help us figure out what kind of test to use. Now as we note this on the chart, we can see that these tests are tests of comparison, and they're looking for differences. So we see the chi-square, the t-test, and the one-way ANOVA, all previously covered in our last couple of sessions. We see these are all difference tests. Now, today we're going to talk about one of the relationship tests. So let's take a look here and note that on this chart, we see that there are different kinds of relationship tests, and we have three listed here. We have the correlation, the regression, and the multiple regression. So this session is going to be about correlation specifically. And like I said, we're going to be talking about the Pearson correlation. Now let's think for a minute about what the correlation basically is. And as we think about it, we want to talk about it being two continuous variables, as you saw from the chart. And when we talk about the Pearson correlation, we're interested in all of that variance being captured so that we can look at the relationship between the two variables. So as we think about it, we say, okay, we need continuous variables to compare, or not to compare, to relate to each other. And then we also want to understand that we're looking for positive, negative, or no correlation between the variables. Now let's think about this for a minute. When you think about a positive correlation, we might have one variable here and another here, and when we say they're positive, we say they move together, just like that. So when one goes up, the other goes up. When one goes down, the other goes down. They tend to go positively correlated, which means that they move together. Now, different from that would be what we call a negative correlation, and that's when one is high, the other's low, or when one is low, the other's high. And we call that a negative correlation. We symbolize it with a negative sign in front of the number, and it helps us understand that these variables move in opposition. We could also say they are inversely correlated, meaning they go in the inverse relationship to each other. And then sometimes we have variables that actually aren't related at all, and we would just say they have no correlation. So as we explore the positive correlation, that's moving together, or the negative correlation, or perhaps no correlation, then we're able to see the relationship between the two variables that we are examining. Now the next clip we're about to see is going to highlight another concept for us to think about, and that is how do we visualize correlation? So let's take a look at this next clip and look at how this is visualized.
The correlation coefficient is this really popular way of summarizing a scatter plot into one single number between -1 and 1. And in this video I'll show you 3 formula-free steps to how that's done. Okay, so I'll work with example scatter plots like this. It shows 4 movies. On the x-axis we can see the movie's length, and on the y-axis a rating for the movie between 0 and 5 stars. The first step for the correlation coefficient is that it fits a straight line to the data. So in this example the line would go somewhere like here. And this is your standard straight line fit, so the one that minimizes the square distances between the fitted line and the individual data points. In the second step, the correlation coefficient simply remembers if the slope from the straight line fit is pointing upwards or if it's pointing downwards. So in the first data set we saw that the slope is positive. And in that case, the correlation coefficient is positive as well. I already mentioned that the correlation coefficient is always between -1 and 1. So if the slope is positive, the correlation coefficient will be between 0 and 1. Then in the second case, in this data set, you can see that the longer movies tend to get the worse ratings, so the slope is negative. And in that case, the correlation coefficient is negative as well. It'll be between 0 and -1. And then there's a third case, and that's that the slope is perfectly straight. In this data set, you can see that there's no real difference between the longer and the shorter movies in terms of rating. And actually, if I draw in the regression line, you can see that it's perfectly straight. And in that case, the correlation coefficient is 0. So just by looking at the sign of the correlation, you already know something about your data. If the correlation is positive, you know that the overall trend is upwards. If the correlation is negative, you know that the overall trend is downwards. And if the correlation is 0, you know that the overall trend is level. So now comes the third step, but this one is trickier. So far, we already know whether the correlation coefficient is between 0 and 1 or 0 and minus 1. But we don't know its magnitude yet. So how big is the value? Is it close to the extreme values, so it's something like 0.92 or minus 0.92? Or is it small in magnitude because the correlation is weak, so it's closer to 0? The correlation coefficient figures this out by looking at the quality of the fit of the straight line for the data. And I'll try to give you an intuition for this first. So here are 3 scatter plots, and I've already drawn in the regression lines. Now, which of these 3 lines fits its data the best? What do you think? Well, so it's this one, because the data fits most snugly around it. And which line fits its data the worst? Okay, so that's that one, because the data scatters the most around it. So in these 3 plots, the highest correlation would be in this plot, and the lowest correlation would be in this plot. Actually, the correlation coefficient for the first plot is around 0.81, and the correlation coefficient for the worst plot is 0.32, so it's much lower. But how does the correlation coefficient figure this out? Well, it compares 2 things. The first thing it looks at is the scatter along the y-axis. So if I draw in the y values, you can see how they scatter along the y-axis. The second thing it looks at is the scatter of the data around the fitted line. So that corresponds to these distances here. And the rule goes like this. The more there's of this in comparison to this, the stronger the correlation coefficient is. Okay, let me show you a few examples. So in this data set, we can see that there's quite a lot of scatter along the y-axis. But there's really little scatter around the fitted line, right? Because the distances here of the data points from this fitted line, they are really short. Okay, so in comparison, there's a lot more scatter along the y-axis than there's scatter around the fitted line. And in this case, the correlation coefficient is really large in magnitude. This is a positive slope, so the correlation coefficient is close to 1. It's actually 0.95, so that's a really strong correlation. And here's a second case. So you can see that again we have quite some scatter along the y-axis, but in this example the scatter around the fitted line is also really large, right? The points are really far away from the fitted line. Okay, so in comparison, there's only somewhat more scatter along the y-axis than there's scatter along the fitted line. So in this case the correlation coefficient is weaker. It's 0.56 actually. That's still decent correlation, but it's less than before. In this third case, the fitted line actually turns out to be straight. So what this means for the data is that the scatter along the y-axis and the scatter around the fitted line, they are actually exactly equal. And in this case, the correlation coefficient is exactly 0. So you can see that if the scatter along the y-axis is much larger than the scatter around the fitted line, then we get correlation coefficients which are really large in magnitude. But if the scatter along the y-axis and the scatter around the fitted line are really similar, then we get correlation coefficients which are close to 0. So now we know the 3 steps of the correlation coefficient. Let's see how this can help us with an example. So here are 2 scatter plots, and the question is, which one has the larger correlation coefficient? So the first step is to fit the straight lines. So they go here and here. And then step 2 is to remember the slope of these lines. Well, they are both positive. So in this case, we already know that both our correlation coefficients will be between 0 and 1. So in the third step, we have to compare the scatters around the y-axis against the scatters around the fitted lines. Okay, let's look at the y-axis first. So in the first scatter plot, we have these y values. And in the second scatter plot, we have these y values. And we can already see that the scatter along the y-axis is larger in this scatter plot. Okay, how about the scatter along the fitted line? So if I draw in the distances between the points and the lines, you can see that they are actually the same in both plots. So now we can make the comparison, because we know that the scatter around the line on the left side and the scatter around the line on the right side are the same. But the y-axis scatter on the left side is larger than the y-axis scatter on the right side. So the left scatter plot must have the larger correlation coefficient. So we've seen that these are the three steps in getting your correlation coefficient. First, you have to fit the straight line. Then you have to remember if the slope is going up or down to get the sign of the coefficient. And in the third step, you get the magnitude of the coefficient by comparing the two scatters along the y-axis and around the fitted line.
So as you can see from the video, there are really two pieces of information that you and I care about as researchers. The first one is the strength, and then the second one is the direction. So let's think about what that is. When I get a correlation back that I have to look at and interpret, I can see that I get a number, and it's point something. And so when I get that 0.50 or 0.85, that's the strength of my correlation. And then the second piece of information is the sign, and that's positive or negative. And so how we think about it is, if you think about 0 on the number line right here, and if you took this side, and this is -1, and then you had this side, which is +1, your correlation ranges between negative and +1, and the closer it is to 0, in other words, the smaller that correlation number, the weaker the relationship exists. So the stronger it is towards a -1 or toward a +1, the stronger the correlation, and then the closer it is to 0, the weaker the correlation. And then when we think about the direction, that's what I talked about a minute ago. When we see that they're positively correlated, they move together. And when we see they're inversely correlated, or we'd say negatively correlated, then we see they move in opposite direction. And we'll take a look at that a little bit further as we go forward. Now, the next thing to talk about is this phrase that I'm sure you've heard a lot. And that's the idea that it's correlated but not caused. Or sometimes you'll hear people say it's correlation, not causation. And so to explore this idea, let's take a look at this brief TED Talk.
Welcome. I came here today to warn you about the dangers of ice cream. You may not be aware of this, but these innocent-looking cones full of sweetness are one of the major causes of drownings. And I've got the numbers to prove it. So if you plot a graph of the number of ice creams that are sold, and you compare it with the number of drownings, you can see there is clearly an upward trend. And I think it's very safe to conclude from this that we should ban ice cream, because it's very dangerous. Since you are all smart people, you've probably figured out there's something wrong with my example. What's really happening here is, of course, that there is an underlying factor, which is nice weather, you might have guessed it. And if the weather is nice, more people will go out swimming and unfortunately drown. And at the same time, more people will buy ice cream. And it's not the ice cream that's causing the drownings. And here it's really easy to see that there is something wrong. But jumping to an incorrect conclusion about causality when you see a correlation is the most often made logical mistake. And today my goal is to make sure that in the future you can recognize this mistake, and I really hope you can avoid making it in the future for yourselves. And I'll do this by just giving some famous examples. And the first one is really rather innocent. The fact is that married men live longer than single men. If you look at the statistics, you see that this is really happening. And women's magazines, they like to conclude from this that marriage is very healthy for men, because it makes them live longer. Well, a friend of mine, he likes to joke that marriage mainly makes life seem longer, but that's because his wife is... But so, can anyone guess what's going on here? Because there is a causal relation, but it's the other way around. The fact is that men who are healthy and rich and well educated and have a much higher life expectancy, these are the men that are much more likely to find a wife. That's the way women are. And the guys who have a very low life expectancy, so they're unhealthy and poor, they are not as likely to get married. So it's the high life expectancy that is causing the marriage, not the other way around. Well, and this, of course, you know, it's not so serious. No one will get married just because he read this. So let's move on to a more serious example. it was also more serious research. In Nature was a study in 1999 that showed that young kids who sleep with the lights on, that they have a much higher probability of becoming short-sighted later in life. Well, and the researchers, they were smart and they wrote very careful that they had found a correlation, and they didn't know how the causal relation might work, but just to be sure they advised all parents to turn off the lights at night. And in the popular media, this became that bed lamps were night abuse, children's abuse, and that it was very bad if parents used lamps in the bedroom. And many parents were worried. I can imagine if this would have happened when my son was sleeping with the lights on, I would have felt really bad. But luckily, the article had to be corrected the next week. And maybe some of you can guess, if there are biologists in the audience, they know. Short-sightedness is genetic. And so it's parents who are short-sighted, and those are the parents who like to leave the light on in the bedroom. And they also are the parents who have short-sighted kids. So again, you know, a simple mistake, easy to make. Then what is, I think, the worst example I know many of them. I see at least one of these in the newspapers every week. But this is a classic one. In the 70s, researchers found that there's a very strong link between kids who do well in school, get good grades, and kids who have a high self-esteem. And they concluded from this that it's very important to make sure that young kids are, raised to be confident and proud of themselves, because if their self-esteem is high, the good results will follow. And this was what was told to parents, especially in the US, for generations, that just make sure that your kid is proud and confident, then all will turn out well. And many years later, someone did another study just to see in which direction the cause was working, and they found that it was in the opposite direction. So the good grades were causing the self-esteem, and self-esteem wasn't causing good grades, and it was even worse. So kids who are raised just to have high self-confidence and not excel at anything, it can be sports or music, doesn't have to be school, but kids who are just proud of themselves and then fail at everything, in the end they will have a very low self-esteem and not be able to make anything of their life. So this was a very serious correlation mistake. And what I want for today is for you to remember that the next time someone wants to prove that there is a causal relation between something and something else, it can be anything. It can be vaccines and autism. It can be female bankers and the financial crisis. And if they point out to you that there is a very strong relation, remember that it's not enough to have a correlation. It gives a very good hint of what might be happening, but before you can conclude that one thing causes something else, you need to know why it does and how it does. So when in doubt, just remember the ice cream. Thank you very much.
Now, as we think about correlation, of course, that is a great reminder that we can't assume causation. So when we think about these variables moving together, in the case of a positive correlation, we wouldn't say that causes the other thing to rise, nor would we say this causes the other thing to rise. We would say they both tend to go together. And we would also say the same thing about a negative correlation. We wouldn't say this causes that to be lower, or this causes that to be lower. We would say that they tend to move in opposition. And so as we see the correlation then, we're aware that we're looking at the strength of the correlation, the number, and we're also looking at the sign, which way the variables operate. And as we get that information, then we know it's just talking about how the variables tend to be related to each other, but not telling us how the causation works. Now, as we approach the Pearson correlation, we want to understand a few assumptions. One is that we're using a random sample. Another is that when we run a correlation, we have to have the data on both variables. We've already talked about how the variables are continuous. We understand also that correlation is linear, and so it's a linear analysis, which is different than, say, like a curvilinear analysis, and that would be a different kind of test. And then we also know that when you run a correlation, you need to have at least 25 pairs of scores. And so what does that mean ultimately? That when we have 25 pairs of scores or more, we're able to look at the relationship. And if you think about that very simply, that makes sense, right? Because if we only ask a few people some information, or only measure a few people on a certain dimension or variable, then we don't have enough to really look at a relationship. And so of course we need at least 25 sets of scores or pairs of scores to make that fair comparison. Now, as we go forward, I want to start with an example that we would use for our class, and we're going to look at the correlation data related to this. We might have a research question where we ask the question, in terms of mediation, is there a relationship between the number of questions that are asked in a mediation session and the length of the session? Now, it'd be tempting to do causal relationships there, but that's not what we're looking at. We're just saying, are the two related? So is the number of questions asked in a mediation session, is it related to the length of the mediation session? And so when we think about that, we're going to use the independent variable of the number of questions asked. We're going to use the dependent variable, the length of the session in minutes. We will understand that the null hypothesis there is that they're not related. And then for our purposes, we're going to look at about 700 cases in the data to understand our analysis. So let's take a look at the data matrix to start this investigation. So as we see the data here, we can see that there's 3 different variables in our matrix. And so the 2 we're interested in this case, is the length of mediation, and then we have the questions asked. Okay, so here we have 2 variables, and the questions asked is going to be my independent variable, and then the length of the mediation is going to be my dependent variable. And here, remember, it doesn't matter what order you have them in the data matrix. You just see that we have 2 different variables here. Now, as we look at it, we can see that the length of the mediation, that's these data here, and it goes all the way down to 700 something. This is our data in minutes. Okay, so we have that in minutes. And that's our dependent variable. And then here we have the number of question asked, and you can see this is just the sheer number of questions, and that's our independent variable. Okay, so we have 2 continuous variables, and we're going to look and see if they have a relationship. So let's go to the next screen, which shows our output here. Okay, so if you ran a correlation, and I show that to you, by the way, on a separate video that you have probably already watched on how to do this on SPSS, but you would get, after you ran the correlation, you would get this kind of an output file. And so here, let's just take a look at what we have. We have length of mediation right here. So that's our dependent variable. And then here we have our independent variable, right? And so we're saying, is there a relationship between the number of questions asked and then the length of the mediation in minutes? And so as we look at this, we see that this is the box that we actually care about. So I want to just show you this. Okay, so there's a reason that you care about this upper box. Notice that it actually matches this box. And that's because it's just comparing it to the other variable twice. So these are the same boxes actually, but we're going to just care about the upper right. So we care about this box right here. And so as we see this, we see 3 very important numbers. So we see this one, which is the correlation number. We say this, which is the significance or the p-value, and then here's the n. So let's take a look at each of those numbers to understand what they are. So let's start with this one. We have 0.340. And so we see a couple things. So one, we see that there is no sign, and so we know this is a positive correlation. Now, I always like to say it's time to use common sense there. Do we think that length of mediation and number of questions asked would be positively correlated? Yeah, that would make sense, that you would ask more questions in a mediation that was longer, right? And vice versa. So one that was shorter, they would trend to go together, right? So we would think that makes common sense. So we see a positive correlation. When one goes up, the other goes up. When one goes down, the other goes down. Then we see the number 0.340. And so we know that this is a significant correlation. And here, because we see the stars, and the stars show us right here that we have a correlation that's actually significant at the 0.1 level. Now, what does that mean? Well, it means that, remember, we had the standard of p has to be less than 0.05. And here, this is saying that we actually have a correlation that's less than 0.01. And this is expressed in this next number down below. So we see this is actually related to this, right? And that's that we see here this number is less than 0.05 and it's less than 0.01. It's showing here on the printout. Okay, so we have a significant correlation. So I usually write significant next to it just to remind myself that, because it's less than 0.05. And I have a positive correlation. And then here's the n. Okay, and this is the n equals 751. So I know there's 751 pairs of scores. And that's kind of interesting to look at as well. Now, one thing you might notice here is that the ends change in the boxes. So you see that we have 751 here, and then we have 753 here. And this means that 753 people answered how many questions were asked, right, in that number of mediation sessions. But here we only have 751 that reported the length of the mediation, right? And so we have to take the lower number. All right, so we see the three important numbers. That's right here, here, and here. And so the next question is, how do we write this up? So let's take a look. It's a very simple process. Okay, so when we are writing this up, we can see that we would start it by indicating the R, and that represents the Pearson correlation. And then in parentheses, we're going to put the degrees of freedom. So that's the degrees of freedom here. Then we'll put the number, and then we'll put the p-value. Okay, so that's kind of the formula. Here's the R, and then the degrees of freedom. We'll put the number of the correlation, and we'll put whether it's significant or not. So let's actually write this out based on these results, and we can use this box right here to express this. And so let's do R, and we'll do the parentheses. And that's the degrees of freedom are going to equal 751 minus 2. So it's that n, and then it's minus 2. So we're going to put 749 right here. And then we're going to put equals sign, and we'll put the 0.340. And then we're going to put p is less than, in our case, we're going to put 0.01 because we saw that it was 0.01 right here. Okay, so where did I get the numbers from? I got this one is n minus 2, which we know is from up here. We know that degrees of freedom is n minus 2. So we have R in then parentheses 749 equals the correlation, which is this number, 0.340. And then we have p is less than 0.01, and we have that number telling us that. So here we can see where we get all of the important numbers for the correlation, and that represents a positive correlation. Okay, let's take a look at a situation where we would have a negative correlation, and we can look at the next slide. Now, the next slide is looking at two different variables. Again, we have the length of mediation, so we can see that here, and we're trying to see if there's a relationship between the average communication apprehension. So let's think about that for a second. The length of mediation is the length of mediation expressed in minutes, and then the communication apprehension is the apprehension score on average felt by the person communicating in the mediation session. And here we see the correlation data just like we saw before. So let's take a look at this. We see now a negative correlation because we can see the negative sign there. We see that it is significant, and we see now we have a lower number, 748 in our sample, where they answered both items, where they answered the length of the mediation and the average apprehension score. Okay, so let's take a look at this and how we might write this up. Now in this case, we're looking at R, and then we're put in parentheses n minus 2, so that's this number. So we'll put 746, and we'll put the correlation in, and that's this number. So here's that one's there. Then we put this one next, and that's negative 0.309. And then I'm going to put that it's less than 0.01 down here, and less than 0.01. And so that is significant, right? Because it's less than 0.01. Now, one of the things to notice, a couple things to notice here actually. So one is that I've taken away 2 to get this degrees of freedom right here. And I have to put the sign in when I have a negative correlation. And what is this essentially saying? It's saying that when the fear is higher, the length of mediation tends to be lower. And when the length of mediation tends to be higher, the fear tends to be lower, the apprehension tends to be lower. So as we're thinking about this, we say they move in opposition or opposite directions. And so we see that. Now, one thing you might be wondering about is this number here, the 0.309, negative 0.309. And as we're evaluating these numbers, one of the things to tell you is that it's affected by sample size. So in a study that involved maybe 20 or 30 people, this number might not be considered significant, but it is significant when you have this large of an N. And so just to know that when you have a larger sample size, it's more likely that you'll get significant results. So that is a different discussion that we could do in a more advanced class that would talk about power and the problems associated with power, and then what adjustments you might do to guard against the power when you have a giant data set. Might be to move the significance down to perhaps even 0.001. And we might do that in cases where we have such a large sample size that we want to be very conservative with the kinds of results that we end up with. So that might be a reason to do that. Okay, now let's go on to the next slide and look at another situation. Now this next example is an example of a partial correlation. And we call it a partial correlation because this is the type of correlation where we might, as a researcher, be interested in a relationship, but we might suspect that there's something that is causing a change in the relationship. So let's take a look at what this might be thinking about. So it's really our first correlation that we ran, where we were looking at the number of questions asked, and we were looking at the length of the mediation. So we were looking at the sheer number of questions asked, and then how many minutes were the length of the mediation. And so we're suspecting, as we saw from the first correlation, we saw a positive correlation. And that correlation was 0.340. That was the old correlation that we saw just between the two. Now, after I ran the apprehension data, and I saw that there was a negative correlation between communication apprehension and length of mediation, I thought to myself, perhaps we want to examine a partial correlation, which means to remove the influence of a variable when we're looking at that relationship. So let's look at this side right here where we see I want to look at questions asked and length of mediation, but I want to control for communication apprehension. So what does that mean? I want to look at the relationship between these two variables, but I want to remove the influence of this variable. And this is very useful for me as a researcher because I might suspect that something is acting in the relationship that I can't see. And so the partial correlation helps me to remove the influence of that variable. So our previous correlation was around 0.340. And here we see we have a new correlation of 0.327. So we saw that it actually went down a little bit, which is kind of interesting. And we see that that goes down because I have removed the influence of apprehension. In other words, the true relationship or truer relationship between question asking and length of mediation is really this number because I controlled for the presence or influence of communication apprehension. And so this is kind of a useful tool if you believe you need to get rid of the influence of some kind of variable. All right. So as we go forward, now one of the things we talked about earlier is that some researchers like to display correlation data by looking at scatter plots. And so I want to just circle forward a little bit on this next slide and have us look at a scatter plot and notice that this is the positive correlation we just looked at. So we have questions asked here, and then we have the length of mediation here. And we can see that each of these dots represents a data point. You see that? So every dot represents a data point. So we could have 700 of these, right? And so as we look at that, we know that every dot here represents a data point. And so, for example, if I had an 80-minute session right here, length of mediation, and 23 or 24 questions were asked, that might be this data point. And then if I had 100 minutes of the mediation, then maybe 50 questions were asked up here. So you can see how all of the data are essentially generated into this set of dots, which are indicating each data point, and that's the paired data that we see on the matrix. Now, the thing that you saw earlier was that this line tends to be drawn. And that's through the data, and that's the line of best fit. Now, there are other classes that talk way more in depth about the idea of the line of good fit. But essentially, what we're doing is we're seeing a positive correlation because it goes to the right. And so we see that's a positive correlation, meaning the data tend to go, we see more up and up, right? So when one is high, the other's high. When one is low, the other's low. And we see that the data tend in this direction. And so we would say this is a positive correlation. Now, if we go to the next slide, we can see what a negative correlation might look like. And here we might have the minutes of mediation again. And then maybe we have the apprehension, because we had that as our negative correlation. And we see that we see more data here on this end when apprehension tends to be high, then the minutes tend to be on the lower end, right? So you can see more data here. And then we see some data here, obviously, as we see it lay out from the matrix. What does this mean? The line of best fit goes that way. And so that shows us that we have a negative correlation, meaning the data trend in a negative direction. When one is high, the other tends to be low, and vice versa. So that gives us kind of some vision into a negative correlation. Now, as we think about it collectively, essentially, it's kind of an easy concept to say, are two things related? We know they're not causally related, but are they related? And if so, how strong are they related? So that's the strength of the correlation. And then we also ask the question of what the direction is. What kind of relationship is it? Is it positive? Is it negative? And then we know more about how those are related or unrelated. Now, when we think about writing these results up, of course, it's difficult not to assign causality. It's something very tempting to do, right? To assign causal outcomes to certain variables. And so as you're thinking about it, I would challenge you to write what happens to the relationship. When one goes up, the other tends to go up or down, whatever your results reveal, and that you would speculate why as a researcher. You might say it's because of this, or it might be due to this other thing. And as you're thinking about it, then you can input your variables into that explanation. Now, if we think about our two variables that are variable relationships that we examined, we could start with that positive correlation. And so as we think about the positive correlation, we think about when the questions tended to go higher, the length of the mediation tended to go higher. When the questions were lower, the mediation was lower. And we can't say that the low mediation, the length of the mediation being lower causes us to ask fewer questions, nor can we say that fewer questions causes us to have a lower mediation. Or a shorter mediation. We just say that they are related in that they tend to go together. And then the second one that we talked about was this negative correlation. And we said when apprehension tends to be high, the length of the mediation tends to be lower, and vice versa. So when the apprehension tends to be lower, the mediation tends to be longer in length in terms of minutes. And you might be able to speculate some different reasons for why that would be the case. But remember, as the researcher, you can't be certain about what the results are or why they are. You just explain what has occurred, and then you can give some plausible explanations. And so as we're cautious about our language, then we're able to do that very task. So that wraps up our show on correlation. And it gives you a little bit of a view into a specific kind of correlation called the Pearson R, or the Pearson correlation. I, by the way, like to think of the R as a reminder that we're doing a relationship test. And so maybe that's a reminder to you to think when you see that little R, you're talking about a relationship. And then as you see that R, then you can examine the two variables that you are looking at. And perhaps you'll do a partial correlation and maybe remove the influence of another variable. But as you look at it, then you can clearly kind of see from a mathematical perspective, are they in fact related or not related? And we look at the strength and the direction to make that determination. Well, that covers our correlation show for today. I hope your day is not just different, but significantly different.